All right, so we've just been looking at the major index. And I'll remind you of what that is now. Maybe, if I can get the pen to work. The major index is the sum over all positions where you have a descent of the position. Okay. There's another statistic we looked at before in class, which is called the inversion number. So the inversion number is maybe a more natural statistic in a certain sense. It's the number of out-of-order pairs. So I less than j, such that wi is bigger than wj. Okay, so these are different. And that's actually a loaded statement. So let's prove that they're different. So let's just do a quick table here of all the permutations of 3. So we have 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. And let's compute the major index. We did this before, so the identity, there are no descents. There's a descent in the second position, the first position, the second position, the first position, the first and the second position. Okay, with the inversion number, we're just counting the number of out-of-order pairs. Well, everything's in order here. The 3 and 2 are out of order. The 2 and the 1 are out of order. The 2 and the 1 and the 3 and the 1 are out of order. And then the 3 and the 1 and the 3 and the 2 are out of order. And now we just chaos. Okay, so what do we notice from this? We notice that these are different. They are not the same statistic. It's not just that I have a more obtuse way to write the one than the other. But the other thing that we notice is that we had McMahon's theorem, which is that the sum over all permutations of q to the major index of w, this is equal to n factorial, the q version. And we also saw, we worked out in class, that that's also the case for the inversion numbers. So this is what we call being equidistributed. And in honor of Percy McMahon, Major McMahon, for the major index, any permutation statistic, so that when you throw it up here, you get this particular q analog of n factorial, is called a Mahonian statistic. So the inversion number is a Mahonian statistic. And what we want to do is we want to understand why. And McMahon was able to give us this nice proof that we went over last time of the recurrence of a bijective proof of the generating function, and we had a nice recurrence relation for the inversion number. But that sort of begs the question: is can we define a bijection that proves this? So what we would need is a bijection phi from Sn to Sn, such that the major index of W is equal to the inversion number of phi of W. Okay, so in 1915 was when McMahon made this observation about the equality of these two distributions. And it wasn't until about 1965 that Dominic Foata answered this question. So we're going to go over Foata's bijection today, which I think is an incredibly beautiful result in enumerative combinatorics. So I'm going to do his bijection by example. And let me start with a nice big permutation. I think I'll take the one that we did in another video if I can find it. 3, 9, 4, 1, 7, 2, 5. And let's go ahead and compute the major index of this. So this will be our W, and let's compute its major index. So we have 8's bigger than 3, 3 smaller than 9, 9's bigger than 4, 4 is bigger than 1, and 7's bigger than 2. So the positions of our descents are underlined. So we're going to add them up. We get 2 plus 4 plus 5 plus 7, and we get 18. So I need to map this to another permutation of 9 such that the inversion number of W is going to be 18. And we can do a quick check that the inversion number for this permutation is not 18. I'm not going to do that because I think it'll clutter up the page, but you should do that. Foata's bijection works with a recursive structure. So going back here to the bottom, Foata's bijection takes a permutation and considers the last letter of it. So W is a word and X is a letter. Maybe I'll make a note of that. Pink seems like a good color. So this is a word, and this is a letter. So for this example, I would think of W as 683947172, and X is the number 5. Okay? And what Foata's bijection does is it has this inner map gamma that depends on the number x and shuffles the letters of W, and then we append x to the end. So whatever I map this example to, it's going to end in a 5. Okay, and the previous numbers are going to be kind of shuffled together. And the base case is that if, as on S1, any bijection has to be the identity. So let me just build up this, the image step by step. So let's start with 6. 6 is just the answer, okay? There is nothing to do here. That's going to be the image. So when I try to append the 8, so I'm going to have 6, and then I'll stick on the 8. And what does the 8 do? Well, in this particular case, the 8 doesn't do anything. Okay, so we're going to leave that one alone. And now I've got 6, 8, and I'm going to add on the last letter, which is 3. So what does 3 do? The 3 looks at everything before it and says, okay, put a bar after, because the 8's bigger than the 3, put a bar after everything bigger than 3. Well, that's everything. And then within the bars, I shuffle things, and there's nothing to shuffle. So again, we haven't done anything yet. It'll get there. So 6, 8, 3, and now let's think about what happens when we add the 9. Oh, the 9's not going to do anything either. So the 9 looks at the 3, and the 9 says the 3's smaller than me, so put a bar after everybody who's smaller than me, and then shuffle things within their bar. So again, we haven't actually seen any action yet, but that's okay. It's coming right now. Oh, as long as that 4 gets done in the right color. So 4. So the 4 looks at the 9 and says the 9's bigger than me, so put a bar after everything that's bigger than me. Okay? And now within each block, what I'm going to do is I'm going to take the number that's bigger than me and move it to the front of the block. So nothing really happens with the 6 and the 8 because they're in blocks of size 1, but something definitely happens with the 9 and the 3. So the word that I get next is going to be 6, 8, 9, 3, 4. And now I keep going, and what's the next letter in my permutation? It's 1. The 1 looks at the 4 and says the 4 is bigger, so put a bar after everybody who's bigger than me. Okay, everybody's bigger than him, so nothing's going to happen here. All right, so let's copy it down. 8, 9, 3, 4, 1. And what's the next letter that we're going to add in our permutation is 7. 7 looks at the 1 and says, hey, the 1 is smaller than me. So put a bar after every number that's smaller than me. Every number that's smaller than me gets a bar after it. Okay? So that means that the end of every block, the last thing in every block better be smaller than 7, and everything else is not smaller than 7. And at the end of the block, you move it to the front of the block. Again, most of my blocks are trivial in this case, but this one's not. So I get 6, 3, 8, 9, 4, 1, 7. And now I'm going to append a 2. And the 2 looks at the 7 and says, the 7's bigger. So I'm going to put a bar. Now everything that's bigger than me gets a bar after it. And lots of things are bigger than 2. So lots of things get bars. And again, the only action is going to happen in this block that's size bigger than 1, but we'll circle everything else just because. And I get 6, 3, 8, 9, 4, 7, 1, 2. And now we're going to get some real excitement when we add on the 5. 5 says 2 is smaller than me, so put a bar after everything's smaller than 5. So 4 is smaller than 5, 3 is smaller than 5, and that's it. And now we circle the ends right before the bars, and everybody at the end of their block moves to the head. That's this gamma map. So here the map gamma, maybe to emphasize this, the map gamma is what I'm doing here. Okay, so what's the permutation that I get? In the end, it's going to be 3, 6, 4, 8, 9, 1, 7, 2, 5. This is the image of Foata's map. Phi of W equals this. And let's just check what its inversion number is. So the 3, I'm going to write down here how many things I'm inverted with. The 3 has 2 smaller things that come after it. The 6 picks up the 4, the 1, the 2, and the 5. Yeah, so it picks up 4 things that are smaller than it. The 4 picks up the 1 and the 2. The 8 picks up the 1, the 7, the 2, and the 5. The 9 picks up those same guys. 1 doesn't have anything smaller. The 7 picks up a 2. And now it's a chance to see if we're right. If we add up 3 2s and 3 4s, indeed, we get 18. So Foata's bijection does indeed take the major index to the inversion number. And it's actually not that hard to see why this is the case. So what are we doing when we do this cyclic rotation here? So if we had a word and the original thing, the major index, we're trying to turn it into an inversion number. So we have a descent here, right? Just think about the end. What are you doing at the end? We have a descent that's going to be length n, right? So here, if we have a descent, we want to turn that into a major index. So what we're doing is we're moving it so we're going to have 2 inversions because the 9's bigger than the 4, and now it's going to be bigger than the 3 as well. So I'm adding 2 things to my descent, and also the 8's bigger than the 4, and the 6 is bigger than the 4. So I'm adding n inversions, right? The total number of inversions that I'm going to get here, I'm going to get the 6 is bigger than the 4, the 8 is bigger than the 4, the 9 is bigger than the 3 and the 4. And that's what I'm getting right here. And if we look down here at when we're doing this last one where we're doing the 5, it's the same thing. Now we have something that's not a descent. So we don't want to add inversions, right? So if I just put the 5 on, I've added an inversion with everything that's bigger than the 5, right? So that would be the 7, the 9, the 8, and the 6. And so what am I doing? Well, I'm stripping away an inversion for each of those guys. So the 6, it's going to gain an inversion with the 5, so it loses the inversion with the 3. The 8 gains the inversion with the 5, so it loses it with the 4. The same thing with the 9. The 8 and the 9 both lose their inversion with the 4 because they gain it with the 5. The 7 loses its inversion with the 1 because it gains it with the 5. And the 2, well, it didn't have an inversion anyway, so we're fine there. So the idea of this inner map gamma is to take the number of inversion, take whether or not I have a descent and make it an inversion. So if x is bigger than, say, w minus 1, then what we're going to do, that's the case where we're not going to have a descent. Then what we're doing is gamma x decrements the inv by, well, let's give that guy an actual length. Let's say w has length k. By k. It's gonna strip out k inversions. Okay? Otherwise, if x is less than wk, then gamma x increments the inversion by k. And that way when I append the number, it's going to exactly keep things static. Okay, so this is a really awesome bijection to consider. There are lots of beautiful generalizations of it that we can consider, and maybe we'll do those in some of the homework.